So Alex Margolin was leading this effort in Mellanox, so I'll give him credit. So we'll talk a little bit about the motivation for this transport we're calling dynamically connected, explain a little bit about it. It's not something new, we've presented it a couple of times. What's new is actually that we have APIs now as part of the RDMA core package. And some additional we'll have to submit in the next coming months to complete the work. And I can explain some use cases. So basically today, the common transports we use are UD and RC. Each one has its benefits, capabilities, and limitations. We talked a little bit about large scale, and we know that RC is limited with scalability. We'll go to UD, but then we lose the RDMA capabilities. We lose reliability. So there are give and take or benefits and disadvantages for each one of the transports. And basically, what we want to present with the dynamically connected, that it takes the good of both sides, both the transports that we're familiar with UD and RC. So DC will supports RDMA, which is like an RCQP. It's scalable because you can send to multiple destinations by having a dynamically connected session, and I'll present this further on. So it's taking some of the RC capabilities, taking some of the UD capabilities with a, sorry about the AD, it's an address handle, and exposing more advanced scalable RDMA capabilities. So this is a high-level semantic of the connection and data path. So basically, software wants to send a message to A and then another message to A. So it will have what we call the responder will have a target, and the sender will have an initiator, DC initiator, sending a message or posting a send message to the initiator. The DC will issue a connect, send a request, send a second request, and assuming the connection and everything was successful, there will be an ACK and potentially an immediate disconnect. So the connection is a very short-lived connection. Hardware will manage the connection in order to maintain the reliability and be able to immediately connect to a different DC target. So on the receive side, this API, first of all, is not symmetric. It's an asymmetric API. So on the receive, we expose what we call a target. One is enough. It can receive from multiple destinations, not at once. So we want to be able to have multiple underlying resources for the DCT. On the send side, DC initiator. How many? Again, we could use one, but then we're blocked. We can't send to multiple destinations in parallel. So more than one is nice, but we don't need to have a full mash of all-to-all. If we're sending at the most 5 parallel messages, so 5 DCI instances will probably be enough. We don't have to have full mash of classic all-to-all RCQP scalability. Internally, as I described, DC performs a temporary connection on the first write. It connects to the remote, the DC initiator will connect to the remote DC target, send a work request or multiple packets in order to complete the RDMA transaction. It disconnects, not always immediately, usually after an idle time. Maybe there's more messages going to be sent to the same target destination. So more efficient to keep the connection open. And obviously what happens now if you want to send to a different connection. So next slide will show how does DC change to a different address. So in this example, we'll talk about the switch destination. Okay, so we want to send to target A and immediately send to target B in this case. So we're talking about the same reliable connection. So DC will initiate a connect to the remote DCT. We call this internally a responder. It will allocate one, get the send operation and acknowledge it. The moment hardware sees this is completed, it will disconnect and initiate another connect to the second destination once it gets the work request. And again, complete the send operation, acknowledge, and disconnect from this one. So we're getting an RC capable, but it can very quickly switch destinations. We don't have to pay the higher cost of reestablishing and tearing down an RC connection, which can be quite heavy when we're dealing with low latency. So obviously there's never only good, there's some trade-offs whenever you do anything. So some of the trade-offs is how do we decide how many initiators we want? We don't want to scale it to n. That's the idea. We want to be able to scale better. So we want a limited amount of initiators. And we don't want them to switch back and forth because we're paying the disconnect connect all the time. It's just redundant and it hurts latency at the end of it. So we want to be able to save that. So we don't want too few initiators. We don't want too many because the idea was to save on scalability. We don't want to reach the power of 2 as RCQP requires for all-to-all communication, but it does require resources. So the limited amount will improve hardware caching and utilization. So what we've seen from practice is that maintaining, holding a pool of DCIs, trying to reuse the same DCI for consecutive calls to the same destinations instead of switching them can help. So using some LRU policy for recycling this. Maintaining a pool of DCIs per destination hash so we can quickly find the correct DCI to use the LRU. And obviously if there's a DCI that wasn't used longer, it's probably disconnected already from its target, so it's better to take that. DC has two main ways that we've implemented for the connection establishment, what we call half handshake and full handshake. The half handshake assumes the connect is going to be successful and immediately follows with the data send, assuming it's going to be okay. Improves latency, definitely on small messages. Shortens the connection establishment overhead even further. Full handshake is very similar to TCP handshake, so we prevent potential race conditions, and we don't start sending until the connection is fully established. Application can choose which one of the handshakes it prefers to use, understanding the fabric, understanding how many DCIs and DCTs it allocated on each part of the application. DC resources, this is a lot of details about the internal of DC, how to manage the amount of responders we want to have on the DCT, on the target side. So DC has a pool of responders. If there's no responder, it means that the hardware cannot send an acknowledgement or receive the packet. It cannot even send a NAC saying, I'm not going to handle this. So it's just going to silently drop the packet. So we want to be able to have some responders to handle traffic and potentially maintain a couple of responders just to be able to send NACs to the peers so they can better react and not just time out on traffic. So that's the NAC thing. In order to do this, we allow the API, the user to set what's the pool size on the target, how many responders do I want to maintain, again, depending on resources and cluster size and parallel messages that we want to send. And there's a minimum DC responders, which is used to just to maintain the NACs. I'm out of resources, I won't be able to respond to this request, please try again later. And if there are, again, no DC responders, so there's timeout, silently drop packet. So in this case, again, sending to destination A and sending again to destination A. We send, hardware tried to do the halfway handshake and immediately follow with a send operation, but there were no, on the responder side, there were no resources available. So there was, okay, sorry, in this case, there was a responder available, so it sent the NAC. So the initiator can wait a timeout and send a new connect request in order to try the send operation for the first one, second one, and receive all the NAC. So we want to be able to maintain a pool of responders just to be able to NAC the connect request, the dynamically connected request. So these are things we presented in one way or another. They're available through the Mellanox package for a couple of years already. We have some deployments going on with these stuff. What's new is that we've exposed this now as an API, part of RDMA core. So to start with, DC is not a spec transport. So it doesn't sound right to have it as part of the IB core. So what we did, or not just for DC, it's something that developed over the last couple of years, is that as part of the RDMA core, we wanted to allow hardware-specific tunings for applications to take advantage. If you have specific use cases where you want to optimize the CQ or allow some special feature in the QP, which might be hardware depending and not necessarily generic for the entire community, so we wanted to allow like a vendor-specific area to tweak things. We also wanted to allow a data path. We noticed that exposing the hardware, raw hardware capabilities instead of exposing the high-level post-send, post-receive API allows writing more efficient code in very extreme use cases. Obviously, this is more complex because you're binding your application to specific hardware, you're learning the specific hardware registers and capabilities instead of using the generic IBV post-send, post-receive. But if you're at a point where you need these extra cycles, removing a lock, doing something more unique, it's very beneficial. So as part of the RDMA package, providers can expose what we call direct verbs, which will allow the vendor to expose specific things for his hardware. So we have hardware registers and definitions which can allow user to write his or read the CQ directly from hardware and not using the IBV poll. That's where this started off. But it's also good for things like DC, where we have unique configuration flags or unique objects. So DV is the way for the application to access unique RDMA capabilities of different vendors. Today, what DV contains is obviously DC. That's what we've pushed. We have some advanced CQ tuning and capabilities that we have on some of the Mellanox different cards, different features. And the main, where this started, is bare metal data access path. What we did with DC, the dynamically connected, is we wanted to allow overlapping. So we allowed the IBV QP to be created as part of our DV API. So you can call MLX5 DV create QP with special flags, but you still get a standard IBV CQ or IBV QP. This allows you to use the standard IBV QP CQ for most of the other RDMA-capable features, even if it's just the standard modify QP, destroy QP, or post-receive, post-send in many other cases. Obviously, in the kernel, DC is not a standard transport, so the IB core will not know how to handle this transport, what fields to verify, the state machine. So for this, we defined a QP type range, which is a QP vendor. It's not XRC or others, it's a different range. Using this QP type vendor, we allow in the QP, modify QP, this is not in my scope, this is a specific driver a QP type, so I'll allow the QP type to be managed by the vendor. I'll just facilitate the creation of this QP through the IB core. So this is the API actually in order to create a QP. So instead of IBV create QP, we use the specific direct verbs syntax here. The return value is an IBV QP, so it can be used in other APIs to access this. The first two structures are the classic create QP type because we wanted the user to, most of the features of this QP are pretty much standard QP types. So we wanted to keep the interface as close as possible. And then we add a specific DV QP attributes, which add the additional few bits we need to map, in this case, DCT or DCI. We have some of the flags and specific DC QP attributes. User can choose which type of QP type he wants. If he wants, again, DC is not symmetric. You have to choose your initiator and your target. So you have to specify if it's a target or initiator when you create it. And that's the DC type. And we have some access keys which are used to allow connecting DCs dynamically connected between them. So I can connect only to a DC QP which has a similar key as to mine. So the API is very similar. It just has to bypass verbs because these are not standard IBV QP types. So creating a QP is very simple. Modify, destroy is regular verbs API. There's no special need for any additional, besides the initiating of a special QP, destroying this QP is with regular verbs. What's still missing on the RDMA core package? So currently, the create returns a standard IBV QP. So modify, destroy is regular semantics. There's nothing new there to expose. Sending on a DCI. So in order to send on a DC QP, we want to have the address handle of the destination peer. Again, it's like UD. So you can do the RDMA semantics. You can do atomic semantics. Obviously, you can do send-receive semantics with the scatter-gather list or the non-continuous memory that Tzachi presented earlier. And you want to have the address handle of the peer, which can change between work requests. That's the special DC feature. So simple would have been to extend the send work request. As I wrote here, it's actually not really possible. If we would have done that, it would have hurt performance for any other QP type doing post-send. It doesn't matter if he has DC capabilities or not. The fact that extending this structure will just hurt performance immediately, and we don't want to increase the structure. So what we're planning on doing is actually doing a post-send refactoring. Currently, there's a single entry into IBV post-send, and that has to break down into the different QP types, different providers, and then depending on the send operation specific you want to do. So there's like hierarchy of about 3 switch cases every vendor has to implement in order to reach the specific operation and tune this. So what we want to do is have a register provider functions per QP type. So if you created, that's something which is besides the DC QP, but is pending in order to complete this effort, the DC upstream. So if you created a UD QP, your post-send operations will be fixed for UD operations. If you created an RC QP, you would have RC QP operations bound to your send operations. So everything will be more tightly bound to the QP you're doing. We want to have separate operations for send opcode. So UD QP doesn't have RDMA. We don't have to allow this function at all. And we can switch another switching for send operations, and we can properly define the variables each send operation will have. And once we do this refactoring, we can also allow vendor-specific attribute setting in parallel to the standard send operation, send opcodes per QP type. So if in the DC type, if the user created a Mellanox specific QP type of DCI, the IBV QP, or maybe the IBV extended QP object, will have different send operations, and the user can use this to go again to the DV header file to do a specific send operation with a DC address handle. So he will be able to pass these parameters as part of the DV extensions, which are part of a send refactoring that we want to do. So first of all, I expect that these two can improve performance of general send operations. We'll be able to better extend additional features and more tune this the send instead of a big send worker structure. Everybody's used to it already, so it seems trivial, but it's less object-oriented. Doing it in this mode is more object-oriented fashion for the send operation. So this is a pending effort that we want to do during this coming year. PulseCQ. So using a DCQP, you have to know, on the responder, you want to know where did this operation come from, because it's not a one-to-one connection. It can arrive from multiple connections. I want to know who's the DC initiator source QP. So today already we have the CQ refactoring, the PulseCQ refactoring with the CQ iterator, and there are multiple getters which are bound on the extended CQ. So this is something that's been around for, I think, 1.5 years now, something like this. So it's very simple to add another private DV getter for this CQ. So once you create your extended CQ, you can also go to the vendor-specific area and ask, I have another getter, give me the DC initiator source address, and you can get all the parameters from your CQ. So obviously, without post-send and PulseCQ are things we have to complete in order for general verbs to be valid. Just exposing the create allows to use the hardware mapping of registers. So in UCX open source project, we have not an example, that's the real code we use there to do the post-send. Post-receive is actually a standard post-receive, but post-send and PulseCQ. So UCX uses the direct hardware binding to the data path and implements it specifically. First of all, it's a little bit more efficient, but there's no API yet to do this through verbs. So if anybody's interested on seeing some of the things inside here, hidden below, DC post-send lookalike, there's an example. That's it. So again, just to highlight, DC has been around for a couple of years already. I think some of our customers are using it here in the room or played with it. And what's new is making this more accessible as part of the upstream APIs inside RDMA core package. Questions? Yes.
I have a couple of questions. The first one is to scale out RC. There's already a protocol that does it. It's XRC. How is this better? So
XRC helps you in the receive, right? You still need multiple senders in order to scale XRC.
Yeah, but...
So XRC solves half of the problem. Here we solve both sides of the problem. So XRC, you have a single XRC context to get multiple connections.
Right.
And here you can have basically a single initiator, single target, and you can scale the whole cluster. You might have cache misses.
But not really, right? Because you always say that you have to handle not having enough, right?
Yeah, but you don't need a factor of n. You need a factor much smaller than n. Maybe 1 is not enough, I agree, but 5 might be enough for a large cluster. We have use cases of large clusters that we've run, and like 5 to 10 DCIs are enough instead of...
So what kind of big cluster is 5 or 10 enough?
In our office, we've done 128. I don't know if you know of larger clusters, right? So probably 128 square ranks.
Yeah, but isn't that XRC? Yeah, but if you want to have it you will have to have a DCI per process, right? Otherwise, you'll have to lock. Yeah, but the question is, isn't the scale of XRC, do you think that it's not enough? Do you have clusters which XRC doesn't seem to be scalable enough? Yeah, but that also has the disadvantage of latency, right? Every time you want to send something, you need to create the connect. And it might fail, and then it will take even... Yeah, but once at the beginning. No, I'm saying there's advantage and disadvantage to it. Just one more thing.
Yeah.
You talked about the direct verbs to doing it for non-spec compliant. The non-contiguous memory that you presented ago is also non-spec compliant. Why is that part of the IBV and not the direct verbs?
So the non-continuous memory is not something that appears on the wire. It's not on the wire. The non-continuous memory looks like a regular RDMA, UD, RCQP packet transport. There's nothing special about it. Any hardware on the other side can work with it. A DC changes the wire protocol. It's not a standard RCUD header, so in that sense, it's not compliant. The fact that you have a local host improvement is different comparing to...
and what's advanced CQ? I don't know. I just saw it there. I don't know what it is. That also affects the wire? I mean, it seems like something are here.
No, in the CQ, we...
is there like a way that... How do you decide
distinguish what's here and what's there?
Yeah.
So some of the cases are clear. If you're going to break the spec, then obviously it's a vendor specific and
like the spec on the wire.
Yeah, on the wire.
Okay.
That's my view. Obviously, maintainers, Jason, I don't know, and Doug might want to. So for instance, we feel that the non-continuous memory, the API that Tzachi presented, is generic enough, and also we have to do some manipulations in order to correctly push this into the hardware. So we worked on exposing an API to have it generic enough so other vendors, can adapt to their hardware. I mean, if there's no other vendor to speak with, it's harder to match this.
Yeah, I mean, if you publish the wire for DC, other vendors can do that as well.
Right. So with tag matching, actually it happened. So in tag matching, there's a big, inside RDMA core, there's a big paper, a big document that explains how tag matching works, how the fields are defined, and tag matching is part of the VERBS header, actually. Okay, so standard RCQP can be worked with tag matching because it's not a spec, but the entire thing is explained there. Any other vendor implementing the wire protocol can automatically use the header file there. So in that case, we did the effort. Tzachi also mentioned extended atomic. So there's a standard atomic 64-byte, and we have something which is non-spec atomic. So we would like to expose this through DV. Again, we don't think it's generic enough. Maybe if other vendors want to participate, and we can define or have their agreement. Okay, this looks good enough. Let's expose it. So it can be done.
Okay, thanks.
I suppose that this is hidden from the application. So if you have multiple applications and each one of them want to open a different number of QPs, they still capable of doing that.
Yeah.
So when they do that, they will post receive buffers and they will post Wookiees, and sometimes they cannot really go to the hardware, so they have to stay somewhere. So these are resources that you need to allocate as well, right?
So I'm not sure I followed. I mean, you have
So say you have 5 DCIs and there are
so the
100
DCI
rows.
has a work queue similar to regular QP. You have to define the depth of your work queue, and if you try to post send more than the DCI work queue because you didn't get a completion, so your application has to maintain this.
Okay,
similar
so each
to a regular
DCI
QP.
is just one work queue, and from different
Yeah.
different queue pairs in the eyes of the application will go to the same one.
Right. So when you post on a DCI, so it has its own send queue depth, and until you get a completion, you didn't clear place in the send queue depth.
Right.
And when you post send, you give the address handle to the target destination.
And same for the receive buffers, I suppose.
Yeah, receive buffer is a standard post receive, and when you get the completion, if you're interested, you have to find who's the source DCI that sent me. That's the extra
Right.
poll. But otherwise, it's a standard poll
So
CQ, and you get the completion.
With a single work queue for a DCI, there could be some blocking or some periods where one application send a very large message. And is there any interleaving or
So
anything like
if
that?
you have two applications, basically you have two IBV contexts, so you're going to have to create different PDs, different MRs, and different DCIs. So every application will still have its own DC initiator, QP, just like it would have its own RC QP. This is not, it doesn't share cross processes. Okay, that's the story I gave yesterday.
So each process needs a single DCI?
Single is the minimum. Yeah, we recommend if it's a big
Well,
enough
at least a
cluster.
single.
Yeah, because what you just mentioned, the blocking. If I send to a DCT and it's bombarded now, so my work request is going to be stuck until it's completed. So if I have a couple of DCIs, I can share. I can do try to manage who's less loaded and pushing that queue. I can reuse depending on targets. So depending on how your cluster is built, how your application, what side of traffic
Right.
you know, you would want to increase the amount of DCIs. One is enough, but we see that more is
This
better.
is then another determining factor of how many DCIs you need, because the number of processes you need will determine the minimum number of DCIs, right?
Yeah.
Okay, thank you.
I'll try to keep this brief. So we're using both on Summit. We're trying to understand when it makes sense to use DC and when to use RC. But one place where I think it's not making sense right now is on storage. So the clients will typically just round robin over the servers as they're writing out data. And so we see bandwidth fall using DCT. Can you mix RC and DCT so the clients are sending RCs for request and then the servers could use DC to do the RDMAs to the bulk transfers? Is that
Yeah.
nothing?
I mean, it would be similar to having like two RCQP connections.
Okay.
So you would use one for part of the protocol
Okay.
that the application is doing, another one for the protocol response, and then you can mix and match.
So if
They can use the same CQ. You don't have to separate CQs, for instance.
Okay. If somebody was to use the same number of DCs as they would RCs, would it consume the same amount of memory, or would it actually be larger because of the extra state that you have to maintain?
I'm actually.
Evaluation with this on the rapid side. So if you use the same number of DC initiators, the performance is not as good as if you use a limited number of.
Not asking about performance. We're still trying to figure out what makes sense. I want to know about memory consumption because we're using. Right. Okay. All right. Thanks.
So are you targeting Rocky or IB with this?
Both.
And in IB, how do you deal with like path record differences between different nodes?
So basically, so you have your address handle per connection.
So do you have to have, go? So it's up to the app to do path record queries to
Yeah.
figure out its address?
Yeah.
Okay.
Okay. Yes. If we have time, last one. Sorry, I couldn't hear you.
You mentioned the management of resources, some cache or some allocation of DCIs for applications.
Yeah, so,
So that's something that the driver or the software need to manage, right?
the application. So we expose DCI as a single resource, and I mentioned that we see that having one can work, but it's not optimized for performance. If the application will hold a couple and it knows what application logic is being done, for instance, he was giving the example of storage, which might be different from protocol, other application kind of protocols. So you would better know how to utilize the initiators, the DCIs. How many do you want to hold, and how to use them. If you're reaching out to a specific target many times, you might want to keep it in a different pool. If you have targets which can be stuck, so you don't want to load. If you know how much load is on each DCI, you can try and load balance the work request between them.
So the application basically allocated DCI for itself.
Yeah, so it would allocate maybe 3 or 4 instead of 1, and have some logic on top of these.
So this allocation is also in the API? I didn't see that.
The allocation of a DCI is there. Just dv create MLX5 dv create QP, and you create a DCI. You can create 5, and then you have to, or the application has to decide the post send, where is it going on, which one of the 5 by some hash lookup, LRU, or some other kind of logic.
Thanks.
Okay. Thank you.